Hello, my name is Josie and my partners Anna and Reese here. For our project, we researched the coin rotation paradox. This paradox can also be known as the rolling coin paradox, the coin rolling on the coin paradox, the sliding coin paradox, and the double rolling circle paradox. The coin rotation paradox can be defined as so. There are two coins on the same side of a flat surface. One of them starts at the top of the other and rotates around it without slippage until it gets back to where it started. The question is, how many times does this rotating coin actually have to rotate before it gets back to its starting point?
This is a seemingly visual paradox due to the nature of how the illusion hits the eye. Most people would be quick to answer that it would only take one rotation of the outer coin to get back to its starting point because the coins are the same size. This is what makes the coin rotation paradox a paradox, because if you break it down and look at it visually, you will see that it actually requires two full rotations of the outer coin to get back to its starting point. But why?
The paradox is counterintuitive. On one hand, it looks like the outer coin makes one full rotation around the center coin. However, as we have come to know, that is false. It is easier to visualize a rotation if there is something on the coin that you can observe, such as the head of George Washington on the quarter. Washington starts upright and rotates around the center coin. You can observe that Washington is back in its upright position when it's at the bottom of the stationary coin. It continues into its second rotation, starting at the bottom and ending back in its original upright position, making two full rotations in total.
It's actually a lot harder than it looks to demonstrate this visually, so here's an external video just to better some understanding.
When you observe with a small object in mind, you can pace your eye.
Another way to imagine this is by using a piece of yarn that is the same length as the circumference of the coin. In this case, we are using a quarter. If you take the rotating coin across the piece of yarn, you see that it only has to make one rotation.
That here. Then I do indeed get to the end of this string exactly after one rotation of this coin.
However, if you used two coins instead of the coin and the yarn, you'd see two full rotations being made. Why is that?
A final way to decipher this puzzle is if you put a coin on each end of the string. At this moment, the coin has already made one full rotation as it has been flattened out equally along the length of the string. Then, as you can see, it makes another full rotation as the string gets wrapped around the stationary coin, adding up to two full rotations once again.
So in other words, the first thing that I've done here is I've just rolled out this coin here. Just rolled it out like this, and indeed, that is exactly just one rotation. So you think, well, now we're through, right? But of course, it's not that simple. Actually, this string is in a circle, right? So in me rotating this string around the circle, you can maybe see that this eagle is also having to turn around one more time.
This formula is used to find the number of rotations that the moving coin will move around the stationary coin. The capital R stands for the radius of the stationary coin, while the little r stands for the radius of the rotating coin. You can add 1 because the coin completes one revolution around the stationary coin. For example, let's use our 2 quarters. The radius of 1 quarter is 0.4775 inches. This would mean 0.4775 divided by 0.4775 plus 1. This equals 1 plus 1, which means that the moving coin will make 2 rotations around the stationary coin.
Now, using an example of a penny and quarter, we are going to demonstrate why these two different coins fit the paradox. The quarter will be our stationary coin, and our penny will complete a revolution around it. You can see that demonstrated here. The rotation of a penny around a quarter can still be applied to the paradox because while it might not be as counterintuitive, if you plug the radii into the formula big R over little r plus 1, you get the number of rotations the penny will make around the quarter. Despite their differing radii, this is considered an extension of the original paradox. Without using the formula, one may assume that the penny will make more than one rotation around the quarter. This is true. However, you will use the formula to find the exact number of rotations around it. By using the formula, you find that the penny will rotate X times around the quarter. You can find this question in the provided worksheet. In summary, coins of differing radii fit into the coin rotation paradox, but will produce a different result than two rotations from two coins of the same radii. The coin rotation paradox is an example of how our knowledge about rotational motion can be deceiving and how understanding the mathematical complexity of it, we can find a solution.
Thank you.